Hello everyone. Well, today I'm going to talk a little bit about the simple pendulum. Now, the reason we're talking about the pendulum is because the pendulum is an example of what we call a simple harmonic oscillator. Now, a simple harmonic oscillator is a system which is periodic, meaning it has a certain period, has a period t, and the period is the amount of time it takes for the oscillator to complete one cycle. Now, we're looking at a very specific or special type of oscillator, and one that is called simple harmonic. Now, the pendulum, in fact, is only a simple harmonic oscillator when the amplitude is very small. But let's look at some of the characteristics of what this looks like. So I'm going to draw a picture here of a simple pendulum, and here this dotted line represents my vertical, and the pendulum is at some angle theta with length L, mass M with respect to the vertical. Now, what makes this system oscillatory? Well, if I release that pendulum bob, what's going to happen is it's going to follow this arc. All right, now in order to discuss more meaningfully the motion here, what we can do is we can do an analysis of the forces that are acting on the pendulum. So one of the forces that's acting on it is a tension force, holding it in place. And then I also have a force of gravity which is pulling directly downwards. Now, what's important to notice here about the force of gravity is that it is actually what's called a component of the force of gravity here is going to be the restoring force, or the force that pulls the pendulum bob back to its equilibrium position. The tension doesn't pull the pendulum bob back to its equilibrium because it's perpendicular to the arc length. It's a component of the force of gravity. So let me extend the line having to do with the length. Notice that this angle here is also equal to theta. So there's a component of the force of gravity that is along the arc, and that is what draws the pendulum back to its equilibrium position. All right, so let me introduce a coordinate system here. I'm going to say that the arc length is S. And right when we're at the vertical, I'm going to call that S equals 0. And the location where the pendulum is located right now, I will say that this is S equals A. A for amplitude. And at this location, we're just going to release from rest. All right, so now my picture has a few more components on it right now, but let's now analyze the forces. So if I was to look at, if I was to apply Newton's second law, Newton's second law says the sum of the forces in any particular direction equals the mass times the acceleration. So let's actually look at the sum of the forces along the S direction. So I'm going to sum up all the forces in the S direction, and this is going to equal M times A sub S. All right, now in the S direction, I actually only have one force, and that is actually just the component of the force of gravity, F sub S, which points in the negative S direction, and that's going to be related to F sub G by a sign. So what I'm going to have here is Fg, which is equal to mg, sine theta, and there's a negative sign here because it's pointing in the negative S direction. This is going to equal to m times the acceleration is just the second time derivative of the position, s, with respect to time. So immediately we notice that there's a simplification here. The mass cancels, m, and I basically get d2s dt squared equals negative g sine theta. Now, let's try to make a few more simplifications in our equation here. I want to relate s, l, and theta. So talking about arc length, s, arc length s is just equal to L times theta. So into my equation down here, I'm going to plug in s equals L times theta. And when I do some simplification, I can basically divide the L by both sides. Another thing that I want to use here is what's called the small angle approximation. And the small angle approximation is that sine theta, if I do a Taylor expansion, for very, very small angles, it's approximately equal to theta. Right, the next term would be of order theta cubed, and so forth. But for small angles, and we're looking in radians here, I can write sine theta as approximately equal to theta. So now when I plug both of these results into this equation right here, I'm going to get, negative g theta equals L. L is constant, it's not changing, so I can take it outside of the derivative, d to theta dt squared. Now dividing both sides of the equation through by L, I'm going to write d2 theta dt squared equals negative g over L theta. So here's the equation which governs the motion. I call this the equation of motion for the simple pendulum. Now, some couple things that are important about this equation is, first of all, it only works for small angles. If the angles are too large, it doesn't work. The equation actually breaks down, right? Because I have to put in a sine theta here instead of a theta. Now, this equation actually describes a simple harmonic oscillator. We would say that theta is actually, theta is dependent, only on G and L. It doesn't in any way depend on the amplitude with which the pendulum is released from. Now, you might recognize an equation like this from calculus, and one way to solve this equation is simply by guessing, right? We could say, well, here's an equation where the second derivative of some unknown function of time gives me back that function multiplied by some constant. Right, so to solve this equation, let's just guess a solution. So the solution I'm going to guess is, what's a function that when you take the derivative twice, you get the same function with a constant and a minus sign? Well, just a sinusoidal function. So that means either a sine or a cosine. So I'm just going to choose a cosine. I'm going to write theta as a function of time is going to equal some theta max. And then I'll write cosine omega t plus phi naught. Now, theta max is the angle that it's released from. That's my theta right here. Omega is equal to square root g over L. That's called the angular frequency. And phi naught is equal to the phase constant. Phase constant. All right, sometimes what we like to say is everything inside this brackets here, I'm just going to call phi, and that is equal to the phase. And the phase I'll talk about more in a moment here. So how do I know that this is actually the solution or the equation of motion for the pendulum? Well, just take the derivative of this equation twice, and you'll see that it satisfies that equation. Now, this doesn't show that it's the only solution, but it does show that it is, in fact, a solution because it satisfies the differential equation. Now, something that's very interesting about theta as a function of time is notice that omega, which is related to the period, we can write that the period t is equal to 2 pi over omega. doesn't depend on the amplitude. It only depends on G or L. So the only way to change the period is to change this force of gravity or to change the length of the pendulum. And this is something that's characteristic of a simple harmonic oscillator. A simple harmonic oscillator is simply one where the restoring force, in this case a component of gravity, is proportional to the displacement from equilibrium, which we can see is true in the small angle approximation. Not true for any angle, right? But it is true for the small angle approximation. That's one of the characteristics of a simple harmonic oscillator. Now, simple harmonic oscillators are very important in nature, for lots of systems undergo oscillations which are simple harmonic in nature. For instance, oscillating circuits, which contain capacitors and inductors. Also, vibrating machinery are oftentimes simple harmonic in nature. So a lot of oscillators can be described as simple harmonic. And these are very important oscillators because the period is very robust. It doesn't depend on things such as damping, for example, or things that kind of tend to slow the oscillator down, because in reality, you know, this pendulum swinging back and forth in the air is going to jostle the air around, and that would complicate the motion. But it turns out that the period is still independent of that damping force, for simple damping. All right, so let's continue on here. Well, now that I know theta as a function of time, I can also write S as a function of time. So S, I'm going to switch to blue here, S as a function of time is simply going to be equal to, well, L times theta. So S as a function of time is, I'm going to say L times theta is, so S max, and I have cosine omega t plus phi naught. Now let's get a little bit of a picture of what this actually looks like. If I was to sketch, well, before I do that, how fast is this pendulum bob actually moving? Well, its velocity v, as a function of time, is going to simply be ds dt. And if I take the derivative of the cosine, what I get is, I get negative omega s max and sine omega t plus phi naught, where phi naught, again, is my phase constant. Now, omega times s max, that's going to be my maximum velocity, or the maximum velocity of the oscillator. You can imagine as the pendulum oscillates back and forth, it kind of hesitates at the edges, but it speeds up towards the center. So its maximum velocity is always going to be in the center. So it kind of makes sense. If I think of position and velocity, these two functions are just phase shifted. Sine and cosine are phase shifted by pi over 2, because when the position is max, the velocity is 0. When the position is 0, the velocity is maxed. Right? So these are related to each other by a derivative. All right, now, another concept here I want to just talk about briefly here is the concept of phase. So phase phi is omega t plus phi naught, and phase constant is phi naught. Now, what the phase and the phase constant do is they tell you where you are in the motion. Or where you are in the cycle. Now, in order to look at this, let me sketch the picture of the pendulum again. Here is my pendulum. Here's the vertical line. And I've displaced the pendulum from equilibrium. Here's the arc length that it sweeps out as it swings back and forth. Here's my s coordinate. And this position right here I'm going to call s equals a. This is I'm going to call s equals 0. And over here, let's say there's no damping, it's going to reach s equals negative a, and the pendulum swings back and forth as it moves. So it turns out that simple harmonic motion, which I'm going to abbreviate as SHM, is a 1D projection of uniform circular motion. So what does this mean? Well, consider an object right now that's undergoing uniform circular motion, and I have an x coordinate and a y coordinate, and I have a circle. Right? Imagine a little ball here that's going around and around in a circle with an angular velocity omega. Right? You could calculate the period based on the angular velocity omega. And let's say that where it starts out right here, I'm going to call this S equals A. Or sorry, this is just, well, x equals A. And then here's x equals minus A. Right? And then obviously when you're up here, this is x equals 0 and x equals 0. So the phase tells you where you are in the motion. So if I release the pendulum from a position of s equals a, I start out with a phase constant of 0. So if I release from rest at s equals a, this means that my phase constant, phi naught, equals 0. Because I'm starting directly at this point right here. Now that phase constant basically tells you where it is that you start. I don't have to just start at x equals a. I could also you could start the motion right in the center, which would correspond to right here, just by giving it a push in the negative s direction. That would give you a phase constant. If it's, let's say it's moving in the negative s at s equals 0, this would mean your phase constant is pi over 2. Right? What if I release it from, from rest at s equals minus a? Well, if I release from rest at s equals minus a, now my phase constant, phi naught, equals 2 pi. Because the object has started in its motion right here. And finally, if it's moving in the plus s direction at s equals 0, my phase constant is equal to 3 pi over 2. Or I could also say this is negative pi over 2. Normally we like to keep our phase constant somewhere between negative pi and pi, but that's not absolutely necessary. We can also say it's between 0 and 2 pi. It's just periodic modulo 2 pi because every time you go around one time, you come back to the same point. So you can always add or subtract 2 pi to your phase constant and you'll get the same thing. So mathematically, what does this look like? Well, mathematically, what this looks like is the following. So let's look at the very first example right here, which I'll call number 1. What this looks like is if I was to plot this motion, I would have, for number 1, I would have s as a function of time. Well, it starts at s equals a. That would just be the following. Right, this would be once I've reached one complete period. And that's related to the angular frequency as follows. So the equation here for s as a function of time is going to be whatever its amplitude it is. We'll call it a that it starts with. So it's equal to a cosine omega t. Right, the phase constant, phi naught, is equal to 0. But the phase, which is the omega t, equals omega times t. So if I look at the circle here, what's happening is this number 1 describes a object undergoing uniform circular motion. It starts at this point right here, and it just goes around and around on the unit circle. And the s-coordinate is simply the projection of where the object is as a unit of time. So let's say after a short amount of time, has elapsed, it's moved to this location. Now as time progresses, you can see that phase grows larger and larger, but it always comes back to where it started after a period. Now what does the velocity look like in this case for number 1? Well, the velocity as a function of time, again, it's just the derivative of the position as a function of time. The velocity as a function of time, after I take the derivative here, I'm going to get v as a function of time equals negative a omega sine omega t. So sketching out what this graph looks like, I would get something that, well, what do we expect the velocity to be when it's at the edge? Well, we expect it to be 0. What about when it's at its equilibrium position? Well, it should be maximum in the negative. By the time it reaches its negative amplitude, it's back to 0 again. Right? And then moving along here, we can see that by the time it reaches its equilibrium, it should be a maximum velocity now in the positive direction, because this would correspond to the oscillator as the pendulum has swung all the way over to this side, and now it's come back. It's moving in the positive s direction. And then as it approaches its maximum amplitude again here, the velocity goes back to 0. So we can kind of make sense of these pictures just by thinking about the motion one particular point at a time. All right, now I'm not going to go through all of these graphs right here, but what you can see is that as I add different phase constants in here, all that's really happening is you're shifting these graphs back and forth. So if I start with a phase constant of pi over 2, that means your graph really is shifted. Well, we could say it has to start either at this point or that point, but it's really this point right here, right? Because as soon as time begins to increase, I'll just do number 2 here as well. I have s as a function of time. And what we know takes place is essentially, well, this is number 2 right here. What essentially takes place here is that this graph has just been shifted to the left by a quarter of the period. So it now looks something like this. Which makes sense because now, for situation number 2, the pendulum has started right at the center here, but it's moving in the negative s direction all the way until it reaches negative a. And then it comes back along, reaches the center again, but now moving in the positive direction, s begins to increase into its maximum, and then it comes back to where it started. So the situation number 2 just describes a oscillator where, so s as a function of time, it looks exactly the same, cosine omega t, but now I have a plus pi over 2. So in this picture right here, I'm just starting, the oscillator is just starting here, moving to the left originally, and then comes back to where it started from. All right, and then sketching let's continue on here and sketch the velocity graph. So here are the marks that mark a quarter period. I'm going to sketch the velocity graph now. Velocity as a function of time. And really, we could think about also just taking the derivative again, in this case, to find the velocity. Velocity is the derivative of the position, and what I get is I get a negative a omega sine omega t plus pi over 2. So when I sketch that graph, I start off immediately, should extend these lines slightly downwards. So when I start off with a maximum negative velocity because it's moving to the left, and then it reaches 0 when the position is at its negative amplitude. It rises again up to its maximum velocity when it's at the center, but now moving in the rightward direction. I have a positive velocity. And it comes on back, and this would be what the velocity versus time graph looks like for situation number 2. The velocity maximum, by the way, that's just going to be a times omega. That's the maximum speed with which the oscillator is moving. Now we can also think about the oscillator in terms of its energy, right? As the oscillator moves back and forth, as the pendulum moves back and forth, it has a certain amount of energy, mechanical energy, and the total amount of mechanical energy is going to be the kinetic plus the potential. Now the kinetic, you'll recall, is simply an energy of motion. This is 1/2 mv squared. And the potential energy, in this case, is a mg y. It's a gravitational potential energy, which describes how far the pendulum, how much its height changes with respect to the ground. And with a potential energy, we're free to set our origin to be 0 wherever we'd like. All right, now finally, so that's essentially all I want to say about the pendulum. The pendulum is just one example of a simple harmonic oscillator. Before you actually begin and actually take some data related to this, let me show you a simple experiment here. Now, what I have on the screen here is something that actually shows this pendulum in action. So there's a few things that I can do with this pendulum as it sits on its equilibrium position. The first thing I can do is, well, let's just have it move. So what I'm going to do is, let's see, I select it. And you can see that there's a protractor here measuring the angles. As I mentioned already, and you're going to examine this in your lab, very large angles, the motion is no longer simple harmonic. It is still oscillatory, it's just not simple harmonic. So I'm going to stop this here. Now typically if we use angles that are less than or approximately equal to 15 degrees, we're in the range of being simple harmonic, because for small angles, we can write our sine theta as theta. So I'm just going to choose small angles like this. And then there's a few parameters that I can change as pertains to the pendulum. I can change the mass. Now notice mass didn't show up in the equation, so we do expect the period to be independent of the mass. I can also change the length. And I can also change gravity. By the way, it's interesting, when you increase gravity, the pendulum oscillates more quickly. So actually, by timing periods on an unknown planet, that's one way you could measure gravitational acceleration, by looking at how much the period changes by measuring it with a stopwatch. So let's say I want to measure the period. I click the little notch here to get a stopwatch. I press play. And I can time the period. Now it's kind of hard to time the period because we need to know where it stops and where it begins again. So what I like to do is I like to start my timer right when the pendulum reaches one of its max amplitudes, right on the edge, and then I count a number of periods. So when it comes over to the left, I'm going to press start. So I start, I count a number of periods. Let's say I do 10, so I don't have to worry about reaction time here. And after I've got to 10 periods, I'm going to stop. Actually, I don't know if I had exactly 10 there. But the idea here is the number that I have measured, I divide by the number of cycles that I looked at to get an average value for the period. That's going to be the most accurate way to measure it, and that, in order to eliminate reaction time. So let me look at a few other features that pertain to the data that you're going to be taking. I'm going to decrease the length again, and let's look at the velocity and the acceleration. I'm going to put this in slow motion just so we can see. So notice that how the velocity vector, that green arrow, is changing as it goes back and forth. One thing that I didn't show you mathematically was the acceleration. That's this yellow vector right here, which is tangential and then goes radial and then back to tangential. Because as the pendulum moves, it actually has a radial acceleration, which is towards the center, and then a tangential acceleration. The tangential acceleration we could actually find mathematically by just taking the derivative of the tangential velocity, which we found. And then the radial acceleration, or sometimes called the centripetal acceleration, is just equal to v squared over r, where v is just your tangential velocity. So in order to actually calculate that vector, what you could do is just find the magnitude of the tangential, well, the square root of the tangential squared plus the radial squared square root. That'll give you the magnitude of the total acceleration vector as a function of time. And same thing for the angle. You could use your vector analysis to find the angle, and that's actually how that vector would be calculated. Now, one thing that I mentioned was that the since this is simple harmonic, I'm going to go back to normal motion again, take these vectors off, is that it shouldn't be dependent on any damping force. And that's something you can actually verify in this experiment just by moving this notch around. You'll notice that if I put a lot of friction here, that would be kind of like the pendulum, sloshing back and forth in molasses. Well, that would be very nonlinear damping, but very quickly it settles down to its equilibrium position and stops moving in this case. But you can actually do an experiment here to test out whether or not the period is in fact independent of the amplitude. That's the characteristic of a simple harmonic oscillator. So for what we call linear damping or non-viscous damping, the period should be independent of the amplitude. All right, so that's it as far as introduction for simple harmonic oscillators. And best luck to you as you work on the experiment and recitation problems for this week.